Hello everyone, a very good morning to all the students who have joined today's lecture of digital communication. I hope my voice is properly audible.
Yes, sir.
Okay, thank you Drupad. So let us take my screen. So we'll begin with a very simple numerical and then we will also cover topics related to different modulation, alternate modulation schemes and the topics of multiplexing, time division, frequency domain. So yeah, I think is this white screen is visible.
Yes.
So this numerical is very simple and it is covering uh, information about the sampling rate, the quantization levels, etc. So the question I am writing is a binary channel with the given bit rate represented by capital R subscript small b. It is given that channel has a bit rate of 36,000 bits per second. Okay, b per s small b. A binary channel with this bits per second bit rate is available for PCM say voice transmission. Okay, now you are supposed to find appropriate values of three things. One is your sampling rate fs, another is your quantizing level capital L, and the binary digits small n. Okay, so this sampling rate you have to find. L as the quantizing levels, and n is the binary digits which are used for those levels, and the given is your FM is given to be 3.2 kilohertz. Okay, so why this is 3.2 kilohertz? Because for obvious reasons this is a PCM voice transmission, and much of the audio range, I mean a very fair quality audio range, maximum frequency components up till 3.2 kilohertz, they convey the maximum energy of the signal. So FM is given like this. So very simple. What will be the sampling rate? Can somebody tell? If FM is 3.2 kilohertz, what will be the sampling rate? So your sampling frequency with this rule.
Multiplied by 2, 6.4.
Yes, very good. So it has to be a minimum of 6400 hertz or 6.4 kilohertz. Now these are the bits per second. Remember, this is the bits per second. So number of bits into the sampling rate should be definitely less than how much bits you are transmitting per second, the bit rate. It should not cross this RB, that is the maximum value of RB, where N is your binary digits. Okay, so it has to be less than the bit rate of the channel bit rate. RB is given 36,000. Fs we have obtained. So putting these values, your N will come around 5. And if the binary number of binary digits you are using to represent the level are 5, how many such quantization levels we can have? L equal to 2 to the power n means 2 to the power 5. So 32 levels. So if you recalculate these Fs for the entire bit stream, remember, given n equal to 5, L equal to 2 to the power 5, then using this Fs, because we have certain number of bits per level. So if we have 5 bits and we have 36,000 bits per second, it has to be 7,200. .2 kilohertz. So this sampling frequency is respect with the maximum frequency component which is there, with the help of which we are identifying the number of bits we require. But again we are seeing number of bits, they are also defining a particular sampling rate. So definitely it will be more than 6.4 kilohertz, because we are not transmitting less number of bits in 1 second. We are transmitting more number of bits per second. So we need to find the exact value of sampling rate, which will be 7.2 kilohertz. Okay, so this is a digital binary channel, means digital zeros and ones transmission.
Sir,
हाँ जी,
sir,
हाँ जी, बोलिए.
sir, how NFS is less than or equal to RB? Can you please explain that again?
So NFS is actually number of bits which you actually require for representing your levels. If that number of bits you are transmitting, considering your actual audio sampling rate, it should never cross your bit rate which is allowed. If it is more than that, means you require more bit rate to transmit the n number of bits representing your audio signal level, because this is channel characteristics. A binary channel with bit rate, this is the maximum value. Is it clear? Okay, so I think it's clear. Next is your, we have seen yesterday, repeaters. We are calling it as regenerative repeaters. Okay, so let me ask someone from you. Drupad, can you listen?
Hello, sir.
Hanji, Drupad, can you tell, based on our last lecture discussion, what is repeaters?
Regenerative repeaters, yeah, only repeaters.
In general, repeater, if you can say. You do not recall? No problem.
No, sir.
Nandan, Kakadia,
Yes, sir.
Nandan,
Sir.
can you tell what is a repeater?
Hello.
Nandan?
Yes, sir. I don't know, sir.
Sir,
Jai Chopra?
repeaters just
Yes, Drupad.
retransmit signals, or I guess.
Okay, just retransmit. So suppose if I do an analogy drawn between repeater and myself, if I if I receive say suppose a packet of files, you know, and I simply pass it on to next party, am I a repeater? No. I will check for the files whether they are arranged properly or whether they are in good shape. I will do
Yeah,
some
sir. You will increase the power of signal, kind of.
increase the power and also modify the shape also. And when we modify the shape, actually we are referring to distortion. So there are two things. One is your attenuation and another is your distortion. So Jay Chopra, can you tell difference between attenuation and distortion?
Hello, sir.
Hanji Jay.
Um, Attenuation, maybe it is some kind of like I'm not sure, but in distortion, it may be some disturbance in the signal or breakage of some like continuous channel at something. I'm not sure exactly.
Brave Desai. Hello. Yeah, there was some network glitch. So, Brave Desai, can you listen? Mr. Brave? Dwarkesh Gohil, can you listen?
Yes, sir, you are audible.
Hanji, Dwarkesh, tell difference between attenuation and distortion. Drupad, you can lower your hand. Let me ask other students also. Megha, can you listen? Nishan Patel.
Yes, sir.
Nishan,
Yes,
please
sir.
answer my question.
Sir, attenuation means we lost the strength of the signal, and distortion
Okay.
is like uh, interference of some noise or like that.
Okay.
Due to attenuation, sir, distortion occurs.
Because of attenuation, distortion occurs. I
Yes, sir.
disagree with you. Anyhow, half of it you have incorrectly. Drupad, now you can answer.
Yes, sir. Distortion is the loss of information and the change in the shape of signal, and the attenuation is the reduction in the signal strength.
Fantastic answer, Drupad. Good.
Thank you.
So, I hope Nishan you have listened carefully. Can you repeat what Drupad said just now? Mr. Nishan,
Yes, sir.
can you repeat what Drupad said just now?
Yes, sir. Attenuation is loss in signal, and distortion is loss in information.
And one more thing he said.
Sorry.
One more point he mentioned.
Loss in information, sir. Distortion.
After that, one more thing he
Reduction.
said. Reduction.
Yes, sir.
No, shape. He said about something about shape of the signal. Okay. Now I hope you will
Yes.
remember, Nishan.
Yes, sir.
So the idea behind asking all of you people is to just wake you from the. Sometimes they get monotonous, no? So feel free to participate. Okay. So attenuation, loss of signal strength, distortion is the change in the undesired change in the shape of the signals. So the regenerative repeaters, what they do, they amplify, first they amplify and then they reconstruct a badly distorted digital signal and develops a nearly perfect replica of the original signal. Why this thing is required? First we have to look at the reasons for that. So the digital pulse, which is passing through a channel or a transmission line, through a transmission line. Now when this word comes transmission line, don't think something is there in this world. I mean, okay, it must be something. It is a day-to-day usage, component. For example, you connected your mobile phone to your laptop using a data cable, maybe a USB type C. That is a transmission line. That cable is nothing but channel or transmission line. Okay, so these are not some hi-fi words. These are something which are relevant, practical. Okay, so the signal which is passing through a transmission line suffers two things: attenuation and distortion. And why it suffers? It is actually totally because of the frequency characteristics of the line. Distortion because of the characteristics of the line, the transmission line. Some of the transmission lines, some of the cables, they are allow certain frequency range signals to pass without any much problem. At the same time, they offer resistance to certain frequency component signals. So they offer, you know, different services to different frequency of signals. So they have a variable frequency characteristic. It is not like that the same cable you can use for maybe for say for mobile communication. If you are using mobile this no data transfer, you are using some transmission line. The same line you cannot use for maybe connecting other devices because it has certain frequency characteristics. Now how do we get rid of it, the outcomes of this distortion and attenuation? For attenuation we have simple amplification, so we use amplifier. For distortion we have repeaters. So repeaters essentially consist of equalizers. So if I draw the block level representation of a regenerative repeater, it is like first your input signal is coming, you know, it is attenuated, you need to amplify it using a amplifier, and you're supposed to equalize it using a equalizer. So equalizer is something which has something to do with the frequency characteristics. We will see what is equalizer. Amplify, equalize, and then regenerator. Okay, this circuit will give you a regenerated output, and the amplified and the equalized signal conveys information about the timing. So we have a timing circuit because we need to derive information at fixed time intervals or time instants. So this timing information, when to sample, comes from timing circuit, and timing circuit derives this information from the actual signal. That actual signal has some portion of it dedicated to timing requirements. So the rate at which you sample, no, like this sampling signal comes from the timing circuit, this one. So let me use blue color. So this will throw some sampling pulses. Here our input will be like this. When we amplify and equalize, we might have, you know, separated signal components like this. At this point, this is a very weak and distorted signal, and then separated. Regenerator, you have certain decision levels. So the manner in which this regenerator works is on the comparator. Okay, so if you have a threshold like this, and the amplified and equalized signal is like this for this much duration, and then it comes again, we compare it with the decision level. If it is more, then you assign certain bit level. If it is less, you assign certain bit level. Okay, so the output of your regenerator will be something like this. I mean, some signal like this. This is the output. Okay, so amplification is quite simple. What is equalization? Have you ever encountered this term, equalization? I think you might have. you might have definitely equalized sound, maybe some audio signal. If someone from you playing with some audio related apps, if someone can tell about equalization. Only, no problem. I'll tell you. Equalizer, as the name, the term itself suggests, you are trying to balance out. You are trying to make things equal. Now, what we are doing to make equal when it comes to our this digital transmission, it is essentially the impact of your channel, which is different frequency characteristics for different frequency signals. So this difference we want to remove. Whatever frequencies which were given less weightage or less or more resistance by the channel, their level is increased so that it comes to a particular threshold value. Similarly, those signals which were kind of given a heavy weightage, they're also bring down to a threshold level. So in a sense, all the frequency components in the signal, they are given level equal in magnitude. So those who were less, they were amplified so that they reach to a so it's kind of a variable amplification equalizer. You can say it is a variable amplification factor for different frequency components. You're trying to make everything equal. You're trying to have your the available frequency spectra having equal power, equal magnitude for all the frequencies. Okay. Now, I hope it is clear. Equalization. Anyone has any doubt?
No, sir.
Okay. So there are, in general, you have equalization. So whenever this term comes, equalization, and if someone asks you which characteristics it is related to, simply tell it is a frequency related characteristics. You are doing something in frequency domain. Okay. So equalization is generally a two-step process. So you perform two kinds of equalization, you can say, in digital communication. First is a fixed equalization. And second is your variable equalization. Fixed equalization, as the name suggests, it considers the attenuation frequency characteristics of the channel. So a fixed value of equalization is there in this stage where the attenuation frequency characteristics is considered. Now this is because of the length of the transmission line. The higher the length of the transmission line, generally it can be in of the order of few hundred meters or few kilometers, right? So based on that length value, right, whether it is 500 meters or it is 1 kilometer, one fixed equalization you need to provide. That is we are calling as fixed equalization. The second equalizer, which is the variable equalization, it is actually more related to the frequency characteristics alone. First, remember, in fixed, it is the attenuation versus frequency characteristics. In second, it is the frequency characteristics alone for the channel in particular. So you provide variable scaling factor, okay, and if any dip or deviation is there apart from your repeater length, it is corrected. For example, temperature as per so based on different other criteria, like for example temperature, and if it is, I mean, so different parameters will come into play. Okay, you need to have a variable equalization scaling factor in that case. So I hope it is clear to everyone. Any is it clear, everyone?
Yes, sir. But sir, can you please repeat in the in definition wise?
Which one
Simply.
is this fixed and variable?
Yeah, fixed.
Okay, so the first one, which is a fixed equalization, what does it compensates for? The attenuation versus frequency characteristics. Okay, at what frequency, what is the attenuation? Okay, and generally it is fixed value for different frequency ranges. In variable equalization, which is a second step, and this is not like mandatory. If there is no impact of temperature, temperature is constant in the ambience in which your channel, the wire, cable, whatever it is lying, we need not have to do that variable equalization. Only a fixed equalization would do its job. So it can be temperature, it can be in certain cases humidity, okay, etc. So when you consider variable equalization, you have departures which are happening because of your, apart from your normal repeater length, which is there in the first case, because attenuation and frequency characteristics are related. Apart from it, whatever is there, you do it in variable equalization. If temperature is say 50 degrees, you have to do a certain level of equalization. If temperature is 30 degree, so it is see these kind of mixed together. Okay, so the signal output of your repeater, so this entire thing, this is what a regenerative repeater, this entire thing is regenerative repeater for a PCM cable system. So as we know, we need timing information so that we sample at the correct time instant. Okay, and the timing information is hidden, or I mean it's already there in the bit stream which is coming. So some portion of that bit stream is dedicated to the timing value, the sampling at the rate at which the signal has to be sampled, something like that. And when you time your sampling pulses, that is there conveyed through a certain range of bits. Suppose 32 bits you are sending, you define a rule that out of 32, I'm using this say 6 or 8 bits of information as a timing information. Okay, like that. And then this regenerator, what it is doing, you can see pulse shaping it is doing. The incoming signal is rectified and clipped. This is clipping, whatever is above this clipped, just have this level. And rectified, I hope you all might have studied the rectification, right? Rectifiers. Yes or no? Am I audible?
What, sir?
Rectifier.
Sir, can you repeat about it, sir?
I hope you all have studied rectifiers in your basic electronics somewhere.
Yes, sir.
है rectification and clipping happens at the regenerator steps. How you can say? You can see This is the fixed level, DC level. Whatever level is there is fixed, kind of DC constant voltage in that particular time duration. And this is happening because of this clipping. You can see originally signal was like this. With certain decision level, we are clipping it. So we are allowing to transmit a fixed constant DC value in a particular time duration. So that is a regenerator. So we can say the incoming signal, which is this one, amplified and equalized, is rectified and clipped. है ना, उसको cut कर देते हैं. I mean, there is circuit which does that task. It's not like we are cutting. Producing square waves. Okay, producing square waves, and we are then finally getting the digital information. So I think this regenerative repeater concept is clear to everyone. So now we go back to our main slide. Okay, so is the presentation visible?
Yes, sir.
Yes.
So delta modulation, we have seen only 1 bit per sample, compare present and past values, and we have to, here I have used plus del this symbol, that this also is there. Okay, plus delta minus delta, like this. If difference is positive, it has plus delta. If difference is negative, it is a minus step size, like this. Okay, this we have seen. Positive delta means 1 1 1 1 1 1 here. Here negative delta means 0 will be there. Again positive delta 1. So I may give you a graph like this and might ask you to create the binary bit sequence looking at the this quantized signal as well as the actual signal. Would you all be able to do? If you have understood, you can score full out of full in certain such cases. Yes or no? Yes, you have understood? Please say something, students.
So can you repeat?
If I show you, suppose this is what we are actually, so this is not there. If I show you this actual continuous signal and then these quantized levels telling you that this is a delta modulated waveform, would you be able to derive the binary bit sequence by looking at this graph or plot? If you say yes, then it's fine. If you say no, I can just once again tell. If with respect to this level, there is a decrease in this level, the minus delta. So it is a bit 0. From here, it is a increment by plus delta. So it is a 1. Again, it is an increment 1. Increment 1. Till this point, it is 1. At this time instant, you have a decrement in your this level. Why? Because of your scheme. The difference you are calculating, and if it is plus delta, it is a bit 1. If it is a decrement, it is a 0. Minus delta you are introducing. Then again it is increasing, so bit 1. So here you can see decreasing till this point. So all bits are 0 till this point of time. Here again these steps, because your scheme is actually trying to catch up with the actual signal shape, right? This is your signal, actual signal, this one, this red color one, and you are trying to convey it through digital means. So one way is PCM, another is delta modulation. Yes or no?
Yes.
Okay. Then this is a block level description, not reading line by line, and I leave this for you people understand, and definitely we will discuss as and when we find any problem. So I'll share this slide with you, and I may ask few questions with this slide, and we'll discuss also this slide in the next lecture. Okay, so this kind of soft task I'm giving you people. This is a delta modulator, one is transmitter, one is receiver. This is the waveform. Again, one more is there. So there are two noises, granular noise or idle noise. Another is your slope overload noise. So granular noise, you can see like this, because in fixed levels only you can move ahead with as with your continuous time signal. So this difference, actual signal was this, but the quantized level is this. So this is kind of noise. We calling it as granular noise. Whereas this slope overload error or slope overload noise is happening because actual signal suddenly increased. So the slope is very steep, you can see here, suddenly increased to high levels. But our system, our accumulator was not able to catch up that fast. Okay, here it was able to capture during this entire duration from here to this point. It was widely deviated from the actual signal. So when this is the characteristics of signal, nobody can control it, right? But when the characteristics of the signal is such that the slope is very steep, means the there are very large transients in the signal, suddenly going up, suddenly going down, our accumulator in delta modulation is not able to catch up. So this noise, this error uh, occurring because of the slope. So we call it as slope overload noise. And both the noises, granular ho or slope overload, they are giving some error. There is some error which we need to take care of. It should not happen that this time duration in between these is so large, means our signal characteristics is such that it is rapidly changing with large amount of deviations, and our accumulator is step size we have kept very small. It will never be able to uh, produce a result where we can regenerate our actual signal. Okay, so that we need to take care of. So I think this also. In adaptive delta modulation, we have some adaptive algorithm. Just remember, we are using some algorithm which will modify this step size. What was the problem here? Here the problem was it was able to increase or decrease in fixed amount, plus delta or minus delta. And that was the only problem where it resulted into slope overload error. Suppose that if some scheme was there where instead of at this point of time where our system anticipated that the signal value is suddenly increased like anything. So instead of having a plus delta, let us have a plus 2 delta step size increase. So you can see it was the quantized value will be very near to your actual signal level, reducing the noise impact or the error value in that case. Such is not the case in the fixed quantization, fixed step size delta modulation. It is there in adaptive delta modulation, where we use certain algorithm to decide what should be the step size. What are those algorithms? There are two algorithms, song algorithm and space shuttle algorithm. I am thinking to give maybe an assignment to just explore any of these algorithms, song and space shuttle, and to find out what is there in these two algorithms which is resulting into a variable step size. How variable step size is derived, and we'll discuss one of these in upcoming lectures. Okay, so this is adaptive delta modulation. Are we good, students?
Yes, sir.
Okay, we are good. Then one more is there, your sigma delta modulation. We'll stop at this slide today. So delta modulation, we know it is a difference between successive samples quantized into two levels based on whether you are adding step size or reducing step size. If you're reducing, it is a bit level 0. If you're increasing, it is a bit level 1. Okay. So we have seen in the block diagrams in delta modulator, we need an integrator at the receiving side, accumulator we are calling integrator, because we need to retain the last quantization level also. On the basis of that, we are either adding to it or we are reducing that level as per our step size increment or decrement. But integrator has its own disadvantage, that it also accumulates the channel noise which is there. If noise is getting more and more, it tries to include this into the integrated signal, the accumulated signal. The circuit is like that. So if you want to avoid integrator here, like this, okay, some are accumulator, this one, this entire thing, this dashed wala, you're calling accumulator, this is integrator. You're going keep on making feedback adding. So if noise is coming more, then that noise also gets added. So your desire will be to place it in transmitter somewhere. So overall system still remains your delta modulation, and when you do so, when you avoid your integrator at the receiver side, it is known as SDM, sigma delta modulation. So whenever this word comes, sigma delta modulation, just think it is a variation in your normal delta modulation where the placement of your integrator is changed, and all these steps we can read. So I think we stop here and we'll cover SDM, DM and ADM in more details in the next lecture, and then moving to multiplexing. But I hope this has prepared a good base platform for you people to proceed further, isn't it? Yes, students, say something.
Yes.
Okay, Drupad, thank you for the response. So if no query is there, I'm stopping to record.